the practical use of the SVD is really in its truncated form. So we will have some matrix X. And we derive a low rank approximation thereof. So if we use, you can think of it as an outer product of your first left and right singular vectors weighted by the singular value, followed by the corresponding terms for the second singular value, and so on. Okay? And I have an example here. In the bottom right corner, you see such a matrix X. And in this case, I have used MNIST digits. So from left to right, we see different instances. So each column of the matrix corresponds to a single digit. And they've been ordered by classes. The class label is not used, but they've been ordered by classes. So you see some, perhaps these are 20 examples or so of each class. And the first class was a 0, was the 1. So we have an image patch. We have a 1. So somebody has drawn a 1. And now this patch has been vectorized in the direction somebody has drawn a 1. And this patch has been vectorized, let me think, from left in lexicographic order. So this is the first pixel, and this is the second pixel, and so on. And it has been scanned, this patch has been scanned row by row until we found the last pixel. And apparently, in these examples, most people just drew the 1 as a single dash. And this is why this single dash is appearing here in these different lines. If you take, the first lines are empty because the 1 started somewhere not at the very top of the image, and the last few rows are empty because the 1 stopped somewhere on top of, stopped before the bottom of the image. If you take the 0, if we now scan across the 0, you see we find some ink here and some ink there. So these features are plotted from top to bottom. You see here the first part of the 0, and then come these, the left half and the right half of the O, the little bit of ink here and a little bit of ink there, and so on. So this was the 1, 2, 3, 4, 5, 6, and those were the zeros. Anyway, this is the data matrix X, and this has, this is of full rank. And this matrix is now approximated in terms of the singular value decomposition. In the top left corner is the approximation with just a single, in terms of rank 1 matrix. So we've used a single left singular vector and a single right singular vector, and multiplying these two will give you this matrix. It's the rank 1 approximation to that. Then comes the rank 2 approximation, and then this is a rank, I think, 10 approximation to the original data. So you see that as you add more and more of these eigen, or of these singular values, singular vectors, you come closer and closer to the original matrix. Now, as I said quickly just before the break, we can multiply out X times X transpose by doing the singular value decomposition. So in other words, the left singular vectors, U are the eigenvectors of the scatter matrix. And this scatter matrix here is of dimension p by p. We can do an equivalent transformation by starting with x transpose x, which is of dimensionality n by n. And the eigenvectors of this entity here correspond to the right singular vectors. Now the eigenvalues are the same in either case. And this has an important consequence. So in practice, you have to decide if you want to deal with the n by n matrix or the p by p matrix. You should build whatever is smaller. So if you have only 100 images with 1,000,000 pixels each, then clearly you want to work with this matrix, which will be 100 by 100, and not with that one, which would be 1,000,000 by 1,000,000, which wouldn't even fit into your RAM. There's another, or the connection can be pointed out in another way, namely if you consider the following matrix. So I stack my observations in this way. So X is the full matrix of observations. X transpose is this full matrix transposed. Those are zero matrices. We can write both in terms of their singular value decomposition. And now taking this matrix vector product, we get 0 and US, and down here we find VS. So, in other words, what you see here is an eigenequation, and the eigenvectors of this matrix are the stacked left and right singular vectors of that part of the matrix. And again, to establish the connection with PCA, we have some matrix X, which we decompose. And so those would be the new basis vectors. Oh, excuse me, those would be the coordinates in the new basis. So those will be the scores. And these will be the loadings. So the loadings, if we look at faces, those would be eigenfaces. Or if you remember this example of mass spectrometric images, then the loadings could be interpreted as spectra. Okay. So this is all very wonderful, except that it's not a probabilistic model. So in general, PCA, as we've described it here, is not a probabilistic model, meaning that, for example, we don't know what to do with missing values. It also can only find linear subspaces. So let's say it finds a redundant approximation to nonlinear manifolds. What I mean by that is the following. If our data is distributed on a funny snake-shaped manifold with a little bit of noise, this is essentially a one-dimensional structure. So single principal component, a single non-linear principal component should suffice to fit this. But since we can only find linear subspaces, we would find two principal components here. We would find one and the second one. There are variants, which we will look at in the future, that can find such nonlinear manifolds. For example, kernel PCA. Also, PCA, as presented, is not robust to outliers, and there are extensions to robust PCA. I now want to address this particular problem here and introduce to you probabilistic PCA. Also abbreviated as PPCA. Now this is a generative latent variable model. Which makes the following assumptions. We have a latent variable. So latent means an unobservable, a hidden variable, C, which is supposed to be distributed according to a normal distribution with zero mean and an isotropic covariance matrix of rank R. So R will be a small number, 2, 3, 4. And then we have the following model on how to generate observations. Namely, a new vector X will be obtained as a projection into higher dimensional space, W, times C plus shift to some mean vector plus a little bit of noise. So W is of, so C itself was of rank R by 1, and W is of rank P by R, where P can be much larger than R. So we generate a standard normally distributed random variable, and then we project it, this is an affine transformation, into a higher dimensional space. We add some shift to it, and we add a little bit of noise. And the noise is supposed to be also be normally distributed with a covariance matrix psi. and in most cases, a very simple model will be used for this particular psi here. Now, when we discussed the covariance matrix week before last, we saw that covariance of W times C would be given by W times the covariance of C times W. And the covariance of C is just the identity matrix. There's a transpose missing. So this would be WW transpose. So a linear transformation of a normally distributed random variable is still normally distributed, and hence we can say that X now follows a normal distribution centered on mu and with a covariance matrix that is WW transpose plus psi. And by the way, I said that typically the distinction is made that the random variables use capital letters and realizations use small letters. I now use small letters for this random variable just to say that it's a vector. So to make this very explicit, what is a random variable here? C is a random variable, and nu is a random variable. And if we take some function of a random variable, this is again a random variable. So X is also a random variable, and it has this distribution down here. So the only part in this model which is deterministic and that we try to estimate is W. There's also a different model, namely a Gaussian process latent variable model. There it's done the other way around, and W is considered a random variable. Okay, so now we have our observations, and we have this model. And what remains to be done is finding the parameters in the model. For a general matrix, for general covariance matrix psi, this is not possible. However, if psi is assumed to be just sigma squared times the identity matrix, then we obtain closed form expressions. Namely, sigma squared can then be estimated as follows. So S, these are the singular values of our original observations X. This small r is the rank, so that's something that you need to put into the model. So the rank r is a design parameter. You need to specify in advance how many dimensions you believe your latent variable has. And this noise level here is just the average of all those singular values that lie outside the subspace that you're looking for. So you can you find a low rank approximation, and everything that doesn't fit into this low rank approximation is averaged across the dimensions and considered as an average noise level. And in this case, so if psi takes the simple isotropic structure, then matrix W is given by the following. where also U and S, those come from the SVD of X. If you admit an arbitrary psi, then there is no closed form expression, and you also then have some rotational ambiguity in your solution. Okay, so what has really happened? The eigenvectors that we find are still the eigenvectors from the conventional PCA solution, but the scores are a little bit different. So essentially what you do by writing down this model is to say that your high-dimensional observations are an inflated low-dimensional Gaussian plus noise. So adding a Gaussian means you convolve with this Gaussian here. And in a sense, by estimating the latent variables, you are deconvolving this expression here. Okay, and the advantage is that you now have a nicely probabilistic formulation, so you can write down the maximum likelihood for this. And it allows you to find outliers not only when they lie outside the plane that you're looking at, but also you can find outliers in the plane. So let's say we're having a model here with rank 2. And let's say that this is your PCA subspace here. So this is your first principal component, and that is your second principal component. And in conventional PCA, you can only find outliers that are far from this plane. So if we have an observation that lies far from this plane, it can be seen as an outlier. However, everything that lies in your principal subspace cannot be flagged as an outlier by conventional PCA. So if we look at this point, which also should be an outlier, if you compute the likelihood of PPCA, you can identify this one, whereas you could not achieve this with conventional PCA. Also, because you can write down a likelihood, you can use an iterative algorithm to maximize it. And this famous iterative maximization is called expectation maximization. And we will devote a whole lecture to this in the future. But I'm not going to do this in detail today. So this formulation affords an expectation maximization estimation. And this becomes particularly interesting in the zero noise limit. So when you assume that sigma goes to 0, in that case, you get an alternation between the following two steps. In the expectation step, you fix the current subspace. And project all observations onto the subspace orthogonally. So the scores in this new subspace are then given by the following. And you alternate this with the maximization step, where now you hold the scores fixed and try to find a new basis that minimizes the sum of squared projection errors. So now we now insert those new scores we had found and estimate this new subspace as given here. And by the way, these two expressions, they are normally used to solve a least squares problem. So you might recognize this here as the expression that you find when you do linear regression. And in essence, this is an algorithm which has been known previously, namely as alternating least squares. So where you always fix one of the unknowns and given that estimate, update your estimate of the other. And well, if you do this computation with a full rank, you would simply obtain your full set of eigenvectors. However, the advantage here is that if you are only interested in a subset of your eigenvectors, then overall this will be faster. In particular, you see that this matrix here, if you look at its rank, so W was P by R, so this is only of rank R by R. And hence C is R by N. And it means that down here you also only have an entity which is R by R. So that makes for huge computational savings if you only need the first few eigenvectors. In addition, a variant of this can also be used to perform rank 1 updates. So if you want to have an online algorithm where you estimate your principal components as your observations come in one by one, you can either do this exactly using rank 1 update formula for these matrix inversions, or you can do it in a neural network gradient descent style by using a magic step size and updating your previous estimate just a little bit by this new observation that has come in. Okay, so bottom line, if you make this very simple assumption on the structure of your noise, so if you assume that your noise is merely isotropic, then you find the same vectors that you would have found in conventional PCA, but with somewhat different scores. So in conventional PCA, to find the scores, you simply project orthogonal on your subspace, and in this case, you compute the conditional estimate of where your observation might lie. And this gives you scores that are a little bit shrunk. The more practical difference to conventional PCA is that this inside affords you this kind of, or has allowed the derivation of this kind of iterative algorithm, and also that it allows you to deal with missing values. Okay, final topic will be brief, so no break. We'll do this in a single go, namely probabilistic latent semantic analysis. Or PLSA for short. This is also a generative model, which has been invented in the context of document analysis. And has since found very widespread use. So even computer vision people have been using this. And this model now really differs in crucial ways from what we've seen before. In particular, this will now yield bases that are non-orthogonal. So this yields non-orthogonal basis vectors, but it gives you all positive basis vectors, or let's say non-negative analogs of scores and loadings. I'm putting scores and loadings in quotation marks here because these are normally only used with PCA. So the generative model proceeds as follows. You first select a document type. With some probability. And what behind this is a multinomial distribution, which is parametrized by a vector of numbers. Then, given this document, you pick a latent class. With a probability that only depends on the document type. So let's say a document type could be an article in The Economist versus an article in the Sun Boulevard tabloid journal. Then secondly, you would pick the latent classes. So if you are going to read an article in The Economist, it will probably be something to do with exchange rates or with crude oil or with recent technological inventions. If it is an article from the Sun tabloid journal, it will more likely be a royal wedding or things like that. Okay, so this is the probability of a latent class given your document type, and how many latent classes you have is something that the user must specify in advance. So you have to put in, when you analyze a corpus of documents, how many latent classes you're looking for. And normally this number is much, much smaller than either the number of documents or the number of words. And then finally, you generate a word count wj with a probability that only depends on the latent class. No, you don't generate a word count, you generate really a single word. Excuse me. Okay, this again follows a multinomial distribution. So multinomial distribution is just a generalization of the binomial distribution. So rather than just having outcomes or 0 and 1, success or failure, in a multinomial distribution, you can have an outcome, so 1 out of k outcomes, for instance, where k would be capital K would be the number of latent classes. Okay, so this is a simple generative model, and it allows us to write down the joint probability. And develop a likelihood which we can maximize. So the joint probability of observing a document and a word would be by Bayes' rule and now we have the first stage here, the document, and the last stage, the word, but we don't have the latent variable in there. So to bring that in, we can pretend it was always there and has been marginalized out. So we can write, we're marginalizing out okay, and that in turn can be rewritten as follows. So we're using Bayes' theorem here again and are writing the probability of Wj given Zk and di times the probability of Zk given di. However, the choice of a word by our generative model depended only on the latent class. So it's conditionally independent of the document if we already know the latent class. So this is just the probability of Wj given Zk times the probability of Zk given di. Okay, and we can then go on and formulate likelihood. So this is the probability of our observations given the parameters. So we have a product here over all the documents and over all the words found, and take this to the power of the number of occurrences of a particular word in a given document. So this is a bag of word representation where we only count how often a word appears in a document without keeping track of where it is in the document. So we're discarding all, if it were images, it would be the spatial information. If it's texts, we discard all ordering of the words. So this is a huge loss of information, but even so, by just looking at word frequencies, you can still extract interesting kinds of documents, or you can still see interesting structure in your data. Okay, and now this likelihood must be maximized with respect to the parameters. The parameters are the parameters in the multinomial distribution. So how likely we think it is to find a particular document type, and more importantly, how likely it is to find a particular latent class in a topic, a latent class in a document, and then how likely a particular word will be associated with a particular latent class or aspect of a text. It's also called the aspect model. Okay, and so again, I'm not deriving the proper EM formula this time, because we will do it in more detail in the future, but I will show you the equations that you can then finally use to maximize this likelihood. So we again use expectation maximization, where in the E step, you compute the conditional probability of a topic given a document and a word simply by Bayes' theorem. Okay, and in the numerator you have all denominators summed over. Capital K is the number of topics. And now we need those two entities. In the very first step, you can initialize them with random numbers or with some educated guess. Given these estimates, you come up with this number, and now we're going to use this in turn to estimate those two. So the probability So the probability of a word given a document type will be obtained by, this is the entity that we've just estimated here. And this is weighted by the observed word counts. So this is just a histogram of how often did a particular word appear in a given document. This word count is really the raw data. So this is what in the previous instances was collected in this matrix capital X. I've now used this small n just to stay in line with the notation used by Hoffman, the inventor of this method. Okay, so that was the first of the terms we need. And the second term and NDI, this is, I should write this out. This is the summation over DI and WL summed over all L. Okay, now I don't expect you to know this formula by heart or anything. The main point of this is to show that the formula are relatively simple. Okay, so it's really 3 lines of code that you can use to iteratively estimate the parameters in this model. And the parameters, again, those are the probabilities in your multinomial distributions that were supposed to have generated the data. It turns out that this is equivalent to a method that was independently proposed, namely non-negative matrix factorization. And non-negative matrix factorization was originally well, shown in a different setting, namely the authors, Sebastian Seung and a colleague, they were looking at a couple of divergences, so a couple of distance measures, Brakman divergences to be more precise, between an observation matrix X and product of 2 low-rank matrices. And if you use as dissimilarity measure this Kullback-Leibler distance, then, and if you optimize for this, then it turns out that this is the same model as using PLSA. However, in their paper, a different parameter estimation strategy was used. So they used multiplicative updates instead of this EM formulation. Okay, I've applied this to the same data that you've already seen. Thanks. So let's remember what this looked like in terms of PCA. In the first row, those were the PCA eigenvectors, and here were the reconstruction in terms of a growing number of principal components. And you see that each of these principal components, well, it's difficult to attach a meaning or an interpretation to them. And now here is the PLSA variant. And it has a very different characteristic. This looks like it captures different parts of a digit. Okay, so in the first row, those are the basis functions that are no longer orthogonal that were found. You see that they're all positive, no negative entries. One disadvantage of PLSA is that if you now decide to use not 20 but 10 components, you have to rerun the entire calculation. Whereas if you have already computed 20 principal components, you can, omit the 10 least important ones, and you are done with or you obtain a more compact representation. Down here is a reconstruction in terms of a growing number of these basis functions. However, the basis functions here, they're not sorted by importance. So I've taken some random ordering, and I've shown a reconstruction here in terms of parts of this ordering. But you know, it so happens that apparently this basis function, they're used to explain the digit 1. Okay, because starting at this point here, it looks pretty perfect. On the other hand, you know, this has trouble with the 4. The 5 looks like a 3 at the end. So, well, this is not to say that it's better or worse than PCA. It has totally different properties. So both the basis vectors and your new coefficients, if you so wish, in this basis function, they are all positive. And there are settings where this really makes sense. I'm again showing this example here. This was the artificial ground truth. Those are the spectra that the algorithm should ideally estimate, and here is how they're distributed in space. This is the PCA solution, and you saw these negative entries here, and there is the PLSA solution. Okay, all positive, both in terms of the spectra and in terms of these concentration maps. They're not identical, of course, to the ground truth. So if you look at this spectrum, you know, it looks different from the ground truth. But even so, the concentration maps and these spectra are closer to the ground truth than what you find with PCA. Okay, here's a screenshot just to show you that, yes, this has been used in image analysis also. So here, apparently, a very large number of images have been put in to find a couple of topics. And this distribution for visual words given the topic was then well, learned on the training set and then used without modification on the test set. And then the latent class, or the distribution of latent class in each image, was estimated, and these latent classes were then used to classify images. That had to be combined with classification because PLSA is fundamentally an unsupervised technique, so it does not use labels. Okay, and some people attach importance to the fact that these are somehow more spatially condensed. So if we had put faces in there, and if we were looking at the eigenimages, you would see that the image is decomposed not exactly into eyebrows and mouth and so on, but these basis functions are much sparser than the ones that you find in principal component analysis. So we've seen two probabilistic models, and it really depends on the data at hand which makes more sense. We had probabilistic PCA, where your latent variable was assumed to be normally distributed, and then you projected this to a higher dimension and you added normally distributed noise. And on the other hand, we had this model where you have a multinomial. And some people think of this method and related methods in terms of a discrete PCA, whereas that would be a continuous PCA. Discrete because here we have a choice amongst a small number of discrete classes. Okay, questions? So the equations that I've written down here in terms of PLSA, they hopefully make the point that it's really easy to use in practice. Okay, it's very easy to code if you want to use anything like it. Yeah, the advantage of probabilistic PCA over conventional PCA is that you can deal with missing values in a natural way. So by missing values, I mean some observations in your data set where you are missing a feature. So in conventional PCA, you would put in a 0, or you would approximate it with the average feature that you observe for your complete samples. But both are not so nice because you don't really tell the algorithm that this is not a piece of information and it should not rely on it. And in such a probabilistic framework, you can implement this more naturally. Okay, so in the exercise, you will get to play with PCA for yourself. So on one hand, study if in one of the data sets shown, it will improve classification performance to map to this low dimensional space, which can be the case sometimes, because by doing so, you lose some information, but you also reduce the dimensionality. So you reduce the number of parameters that you need to estimate in a classification setup. And for those of you who want, you can download this raw data from this satellite measurements of nitric oxide around the globe, and you can try and produce well, plots or a movie similar to the one you've just seen. Okay, and next week we will move to neural networks and look. So neural networks are no longer used very much as production tools, but they've still offered some important insights as to why it helps to map questions into a higher dimensional space. And this is something I want to explain to you next week. See you then.